introduction, and I have a bunch of slides which were talking about the intro about sort of background of myself, and so this is a paper from 2015 where we were converting NLP tasks and modeling them as basically saying, hey, if you can do language modeling very well, you can solve these NLP tasks. So fun time how in 10 years we're going to change language modeling now. And about the company, currently 5 people, lots of great background, and we are focused on AI agent optimization, and that is basically where the multi-objective RL comes in. So in order to basically talk about something with a topic which can be as academic as multi-objective RL, but happening in production, we kind of have to straddle 2 different types of delivery. One is you can be sort of very theoretical or conceptual, and the other is when you're talking about very nitty-gritty real-world problems like optimizing the marketing email AI agent. So I'll try and do both. I'll first just start by motivating the problems by talking about some of the real-world problems that come up, and really talk about why multi-objective or sort of dense rewards are even useful to talk about. The motives for multi-objective RL are basically things like alignment, like capability versus safety, helpfulness versus harmlessness is a very classic data set in this space, cost versus precision, creativity versus hallucination, and of course from classic ML, recall versus precision. All of these can be framed as like a multi-objective problem, and these are some case studies where we have seen the value of framing the problem as multi-objective problem. So for example, this particular example is talking about how when you're trying to optimize, let's say, an email agent, so it's an agent which has to write marketing emails. It can either, you're gonna have like multiple downstream metrics. Your first metric may be email open rate. Your second metric may be email, whether the person follows through on the call to action, like do they click on the link? Do they actually go to the website and convert in some sense, complete the purchase? And so you want to be able to feed in all of these different rewards for the email that was generated back into your agent so that it will optimize both of these tasks. For example, the email open rate might be more determined by how well the subject line is written, and the call to action may be more determined by the content which is more inside the email once they see it after opening it. So framing these problems as a multi-objective problem actually leads us to we were able to achieve a much better final outcome for our customers. And I'm going to skip this particular case study in the interest of time. I will go over some of the common objections that, or I would say like maybe even baselines, strong baselines to consider. So these are basically, like first example would be that a bigger LLM and a better prompt can sort of fix any problem, right? Basically, complex prompts end up looking like rule engines. So like rule 1 may be, okay, your marketing email, if the recipient is Indian, maybe you will say namaste. And if the zip code is Sunnyvale, then it has a high probability of the person being Indian, you apply rule 1. And if the user is angry in your chatbot, like in your voice agent, you apologize twice. And this obviously it works till it doesn't, or till it becomes brittle. When you think about migrating from like your ChatGPT 4.0 and GPT 5 comes out, and it's cheaper, but it uses a different prompt format, and you're not sure how to migrate. And so basically the issue is you're writing rule engine kind of rules, it isn't learning, and it's brittle, and it kind of stay brittle. And that's about it for this. So the next sort of method that people might say is, why can't you just do something like a F1 score? Precision and recall, obviously F1 score is very well known. You can also do something like a data mixture, where you say, hey, okay, 20% of my data that I'm going to train on is going to be focused on safety, 80% will be focused on accuracy, or you might frame it as a constraint optimization problem, that I'm going to maximize helpfulness as long as I meet a certain bar for harmlessness. The main issue there is that the iteration loop is kind of brutal, in the sense that you what happens is that you have a big disconnect between sort of in a company like the product managers and the engineers who are running the training. And every time, let's say, a PM or a business person needs to see what will be the impact, or like what will be the change that will happen because of focusing on or optimizing for one metric at the cost of the other. You have to redo a training loop because you're going to have to change some of the training recipe. And so that basically makes iteration much more costly, and it delays basically your launch. So let's say you are really trying to figure out, okay, like how much data should I be putting in my recipe for safety? And if I do index too much on safety, would I now be sacrificing my accuracy too much? Those are the kind of sort of counterfactual questions that you really don't get to answer very quickly if you just focus on hard code your training recipe like constants. And of course, I mean, if you have a lot of compute, you can just compute everything in parallel. But you're talking about situations where you also are conscious of the cost of training. And then one more sort of common baseline to go over is like the retry loop. So we all know about scaffolds like React, and there are many more versions of it, tree of thought, chain of thought, etc. Which basically kind of look like this. So here's a shell session where I'm trying to query from some table, where my SQL engine, which in this case is DuckDB, is going to give me a very informative error. It's going to say, hey, Dumbo, you have written the table wrong. And then the next one is going to say, hey, your column name is incorrect. And finally, I incorporate that feedback from my environment, and then I'm able to actually come up with the right SQL, and I get the final answer. So this can be, of course, encoded as a React loop. So you have the thought, I need to do something, I take an action, I see observation from my environment. And this works really well for agents which are working in environments which are sort of non-stochastic. So it basically, it's non-stochastic, and your environment is very patient with you and like willing to give you very rich feedback for every action. So let's say if you're working in something like ad optimization, you don't get, first of all, rich reward, and second of all, even the best action only has a less than 50%, maybe 10% success probability. So if you try to put something like a React loop on a problem like ad optimization, you're going to see like 9 times out of 10 you're failing. So you're going to be doing like basically, as many papers talk about, you're going to end up basically, your model is going to end up learning to hedge or like keep rethinking and redoing the steps a lot. So it will say, okay, it didn't work, let me try something else, basically, because of the high variance of the strategy, you really have to actually use methods that are going to sort of be able to deal with uncertainty and evaluate different strategies where success probabilities are not like 90%. So these are the sort of common objections, like, or issues or baselines to consider, which sort of now tell us, okay, like, assuming that we are past all these points, that we have tried all these things and they're not working, what are the methods for multi-objective RL that we can try. So I'm gonna go over more like a survey kind of talk, and pick very few papers to go slightly deeper into. But I'll try and cover these four sort of overall topics. So first one is sort of task arithmetic, task or load arithmetic. Second is what I'm calling plug-and-play reward models. Third is called conditional language policies, and fourth is I'm calling quarterback models. Basically, it's like models which are used to choreograph your multi-agent systems. So there's a fairly rich sort of like research area in task arithmetic methods. One of the most famous papers came in ICLEAR 2023. Now there is even theory which is coming up in ICLEAR 2025. There was a paper talking about provable effectiveness. I'll go over what the method is. And then there are I think 4 days ago there was a paper from Meta which talked to called supermodel, where how simple arithmetic can unlock state of the art LLM performance. This paper is from CVPR this year. This one actually is one of I like the most, in terms of feeling very generalizable. But overall, the idea of task arithmetic is very simple. It's literally the most basic elementary school vectors you think of. So what they say is you have in task arithmetic you have your initial parameter for your neural network. We are going to train that neural network on a small amount of data. This is in the post-training stage, either you're doing RL or maybe you're doing SFT, but you're really doing fine-tuning on not a whole lot of data. And so you're going to get a new parameter vector after doing the training. So this is what is called theta nu. And what they're saying is basically the delta between these two is a task vector. And the whole idea in task arithmetic is that you can add and subtract these task vectors. So you take task 1, which may be trying to optimize, let's say, something for, let's say, optimizing the email subject line. Task 2 is optimizing the email body. You can basically train 2 different models, and then you can actually do arithmetic on the task, on the task vector, which is just deltas. At first, it seems like kind of a crazy thing. There is some precedent for it. I mean, one of the most famous papers on embeddings was Word2Vec in 2014, where they had similar vector arithmetic, but it's still very counterintuitive that it should work. However, empirically, it has been seen that it does work pretty well. So this is a figure from the task singular vector paper, where what they show is that on 8, on a sort of well-known, fairly commonly used benchmark sets of 8, 14, and 20 tasks, a simple strategy for merging these models can give you almost pretty close to 100% accuracy, where the 100% is measured as what would happen if you were to train a model specifically for that particular data set. So basically every radial, every radius that is intersecting the circle is one model that you're trained only on that particular data set. So there will be 14 different models you would have had, and the region that is covering this entire circle, this is covered by a single model. So a single model is able to get to something like 93 to 95% of the accuracy of these 14 different models that you would have gotten. So this is basically the idea behind the task arithmetic or LoRa arithmetic type of work. Um, we have also tested it ourselves on some of the here I show only toy data sets, where for example you can have one prompt where the prompt is to write a Python function which solves a math problem, and so you can train a model to solve the to create Python function, and train another model to solve math problems, and just by tweaking the weights, you can like in a second you can get like you can change the behavior of the model, and sort of in a very interpretable way. Um, so you change the weight on the code model to be 1 and math to be 0.8, and the answer looks much more like code. Whereas if you were to put like slightly less weight on the code and put more weight on the math, then the code actually starts like hard coding some of the things, and most of the logic is still happening in the comments. So it's a fairly interesting thing that you can change the behavior of the model this way. Do have a video, but I think I'm quite over time, so I'm gonna skip the video and go to the next part. So this is the second part, which is about sort of plug-and-play reward models. So there are really two things I'll talk about here. So reward models are obviously a very standard part of doing reinforcement learning. However, interestingly, even the infrastructure for doing many different kinds of reward modeling is not that freely available in many popular libraries, such as Llama Factory World, OpenRLHF. So they do not support, for example, outcome reward models. They may only support like preference reward models or a specific variant of the process reward model. And I'll describe these in the next slide. And the other thing is that they may not support all kind of the best state-of-the-art algorithms for doing the reward modeling. And they can often be, like the state-of-the-art field can often be improved by using ideas which are already there in other papers. This may just be an artifact of the fact that the best ideas are not being published anymore. Just in this particular first table, which is taken from the Open RLHF book, this table is basically talking about what different types of reward models are, and I will just summarize it myself. So there are obviously preference reward models, which are reward models that compare the outcome of you give the reward model two different like completions for the same prompt, and it has to give you the best outcome, or like pick the best better outcome out of the two. Then there can be outcome reward models, which are you take a task and a completion, and then you have to predict the correctness or like probability of correctness. So this will be in the case of RL with verifiable rewards, or in the case of math domain, these will be the kind of things that are maybe like done through heuristics or through string matching, or maybe you run the final code that is generated against unit tests. But let's say you're doing like marketing, again, like I take the case study example, marketing email optimization, then you would actually have to train some kind of a model. In the old days, you might have trained a boosting tree. Now you might just train a reward model based on LM, like train the final head, etc. So these are basically the outcome reward models, and then there are obviously process reward models, which are really more like you have a chain of thought thinking model, and at every intermediate step you're getting a reward. And then finally you have the sort of the value function, which is it can predict the accurate like probability of what will be the expected reward given the sequence or prefix of tokens that have been generated so far. So there are these sort of four different types of things that one might want to do or one might need. And of course we have made some changes that we hope to upstream to build these kind of reward models in different libraries. And the table on the right hand side sort of shows a table from the reward bench 2 paper, which compares many different state-of-the-art algorithms for reward modeling. And the second paper actually is quite interesting to me because it's not trained, it's sort of the only sort of open source model, which is, at that time it was sort of competing against Gemini 2.5 Flash, and it was not trained on a whole lot of data. So the main benefits there were coming from the reward modeling method itself. And so the QRM method it's basically using quantile regression on top of a multi-objective reward model, which is the R-model. So I'll spend some more time over here on this particular slide. So the R-model paper was quite interesting. What they did is they trained what I can only call reward heads, where they had a regression layer, which was basically trained to predict different aspects, sort of explainable aspects to measure the quality of the LLM's output. So helpfulness, correctness, coherence, complexity, and verbosity. And then in order to convert that these multiple heads into a single score, they had a gating layer, which was basically just a very simple multiplier weights that are applied to each of these rewards, and then you get the final score. Then the QRM basically, instead of predicting the mean values, it predicts a distribution by predicting the quantiles, and then the QRM does a slightly better weight averaging. But to me, the interesting part is in sort of the decomposition of the reward into these multiple factors. And the even more interesting part is our model itself only trains the final layer, regression layer, literally using bridge regression. They freeze all the other parts of the model. There is not even any LoRa that is happening in there. But we know from, so this is another paper from iClear 2022, we know that this can be improved, this type of recipe can be improved readily by basically doing what the Armorum paper did as the first step, and then doing fine tuning on top of it. So this particular LPFT paper is from, like I said, iClear 22, and what they did is they basically did an ablation or did a comparison between how should you do sort of fine tuning for in this case, I guess, you can say training reward models. And what they found is that this recipe of where you first sort of do the rich regression or do the linear probing, get the final head, and then do the fine tuning later on, gives you sort of the best of both. Gives you much better results than doing either of the things alone. And so you can sort of take that LPFT recipe, apply it to Armorum, apply it to the QRM, and then get somewhat slightly better. So there is basically a lot of room left, I think, at least in the open source world, for just doing better reward modeling, I feel. That basically, when we do that, what happens is that you're able to take in sort of many different real world use cases, such as this, the email optimization one, and you're able to achieve fairly high AUC in predicting sort of real world events, downstream events. So you can get like, a fairly high AUC with less than, 5,000 data points for training. So this is, I would say, basically like what I'm calling like plug and play reward models, basically taking the best of the research, sort of putting them into practice. Uh, Finally, I'll talk about the conditional language policy framework. So this is a paper that was actually out by Google in 24, and it's sort of, I feel, overlooked paper, where what they showed is basically very clearly they show the sort of difference or benefit of, and even a new method for doing this sort of multi-objective language modeling. So in this particular figure, what we see is that they're trying to optimize a model along two different axes, or like along two different tasks. So one is that they want the model to perform better on the natural language inference task, and the other is this metric rouge, which I think might be for machine translation, or I forget actually like exactly which task it was for which they were measuring rouge. But the basic idea, the most important thing is, what they show is that if you just try to do fine tuning using their method and just changing the prompts, the steerability that you get, or like the amount of exploration that you can do in the final model is much more limited. So the exploration is what you see in the red figure. Whereas if you do parameter merging in the, if you do sort of this multi-objective optimization in the parameter space as well as the prompt space, then you can actually push the Pareto frontier much further, and also you can do a much more, you get a much more steerable model where you can like really, really push the model to, give much higher result on NLI, let's say, at the expense of the other metric. So you get to really steer the model and have fine weight control over what the model is doing. So I will, there are more obviously experiments in the paper talking about what happens if you try to merge three different models, and what this figure is showing is that basically using a conditional language policy gives you much better results than prompting. And we believe that these results will also hold when you're when you are adding even more tasks, more than three. This is, I won't go into sort of the details of this paper. I wanted to sort of give a taste of sort of the kind of work that is being done in this area. Finally, I'm talking about quarterback models, again sort of driven from a practical concern, which is that most people do not have the ability to fine tune the models that they are doing in principle. Most people who are building AI agents are building AI agents on top of an Anthropic model or an OpenAI model or something where they do not actually have access to it, they can't train. So what do you do there? Right? Are we then only stuck with the sort of rule book driven or prompting driven workflow? Is that the best we can do? And there are obviously methods that can be used to optimize the prompts, and DISP is a very popular library, and the JEPA in vitro algorithm in there are very well used and known. And a slightly more evolved approach to that would be what is presented in OpenEvolve. And these are obviously great, I believe, starting points. But I think what people are now, what research is trying to say, or what many people are trying to do is to have a sort of a choreography model or like a quarterback, which is, basically changing the play for every scrimmage. It's changing what routes players are playing, and or in this case, like what are the prompts that every agent in your multi-agent system doing, depending on and it's changing for every um, new user. It may be changing for every new customer who's building an agent. And so there are two papers that have come out fairly recently. So the How to Train Your Advisor is from October this year, and Prompt R1 is November, 2nd November this year. And the basic idea is quite simple. It's basically, we know if RL is working, we know how to do RL. Why can't we just take the agent, the prompts and the thinking level and what is the exact hyperparameter being used in your agent, take all of that as a config that is being generated by by a smaller LLM that I can control. And then I feed the reward for whatever the final agent is doing. I feed that reward to my steerable agent. So I basically pass through the reward, and now I have converted the problem of string optimization to a parameter optimization problem where I can get gradients. And that is basically the idea in this paper. We have, I think I'm gonna, this is a figure from the paper which I won't have time to go over. But yeah, like the overall idea is described. So in conclusion, multi-objective optimization is a good framework for real-world problems. Prompting or MCP or React at the beginning, not the end. Solving for multi-objective RL also forces us to solve like single objective RL in a more scalable fashion. Like you end up thinking a lot more about how do I build nice abstractions for training multiple different reward models, and how do I serve them, how do I do training with them in the loop, like where your reward model is also hogging up resources on GPUs. And methods for steering black box models, which is a quarterback, can obviously be combined very easily with RL and multi-objective RL. So that's the end. Thanks for listening.
You're also hired.
Does anyone have any questions before we end the night? Cool. Well, thanks everyone for coming. Feel free to grab some food on your way out. There's plenty of salad and pizzas left.